Question 2, we've got time of flight mass spectrometry is an important analytical technique. We've got a mixture of 3 compounds analysed, and we've got the formula of each of the 3 compounds. First of all, describe how the molecules are ionised during electrospray ionisation. So there's 2 kinds of ionisation. There's one where you just use electron impact, use an electron gun. It just removes an electron physically. Or electrospray is a bit more of a gentle technique, usually used for large molecules that you're afraid might get broken up or fragmented. And what you do first of all, you take the liquid sample and dissolve it in a volatile solvent. A volatile solvent is one that's got a low boiling point, something like water or methanol. It helps if it's purified at first and if it's polar, the solvent that you're dissolving it in, that is something maybe like water or methanol that's got delta plus and delta minuses. Polar bonds and hydrogen bonding, but you get the marks saying the liquid sample is dissolved in a volatile solvent or a solvent with a low boiling point, and then the solution is injected into the mass spectrometer through a capillary needle. Capillary needle is a needle with a hole going right the way through it. You get the marks actually for just saying a needle, and a high voltage applied. It's actually applied to the end of the needle, but a high voltage applied as the solution is injected through a needle will get you the marks. And then importantly, you need to say each particle coming out, it comes out as a very fine mist incidentally, gains a proton or an H+ ion. Give the formula of the ion that reaches the detector first in the time flight mass spectrometer. Well, it's going to be this one. It's going to be the lightest one. The lightest ones travel the fastest and we're going to hit the detector first. C3H5O2N. But remember, it's gained a proton. It's gained an H+. So it's now C3H6O2N with a plus. The sample of a germanium is analysed in a time flight mass spectrometer using electron impact. So this is what I mentioned before. Electron impact is just removal of an electron. So it's germanium. It's got to be a gas and goes to Ge plus gas and electron. In other words, it's the first ionization energy of germanium. So all an electron impact ionization is you have something called an electron gun which fires high energy electrons across the tube, and those electrons hit this molecule and just knock off another electron and form a Ge+. But the problem with that is it can fragment big molecules, but for something small and atomic like this, that's not going to be a problem. But nowadays electrospray ionization is usually used. In the time flight mass spectrometer, germanium ion reaches the detector in 4.654 times 10 to the minus 6 seconds. So I've got the time, I've got the kinetic energy, I've got an equation. Kinetic energy is half mv squared as well. So from the kinetic energy, maybe I can work out mass or velocity. The length of the flight tube is 96 centimeters. That's an issue because it should be in meters. So I'm going to have to convert that into meters by dividing by 100 and turn it into 0.96 meters. I've got the mass. No, it just tells me that the mass. I've not got the mass. I've got Avogadro's constant, so the number of particles in a mole. Let's see what we can do then. I know that kinetic energy is half mv squared, so let's start with that because I've got a value for half mv squared. It's 2.438 times 10 to the minus 15. So let's multiply both sides and get rid of that half. Multiply both sides by 2. So 4.876 times 10 to the minus 15 is mv squared. I can't do much else with that because I've not got the mass and I've not got the velocity, so we'll just leave that there for now. Length or distance of the tube is 96 centimeters. So if I divide by 100, I turn centimeters into meters. So let's divide by 100, 0.96 meters. So this tube's got to be in meters. It's very nearly a meter, 0.96 meters. Now this is something that you need to remember. Velocity is distance over time. Think about the velocity of a car going at 30 miles per hour. 30 miles per hour. 30 miles. Miles is a distance. Hour, time. Per means divide by. Miles, distance, divided by per hour. Distance divided by time. That's the way to remember that because you're not always given it. The distance is 0.96 meters. We've got that into meters now. We've got the time. You've been given the time here. It's got to be in seconds, and it is in seconds, so I don't need to do anything with that. 206,274 is the velocity. It's going very quickly. So v squared, if I'm going to substitute in here, I can square it. 4.25 times 10 to the power of 10. Now then, I've got this. 4.876 times 10 to the minus 15 is mv squared. I've just worked out v squared, so I can substitute v squared in there, and I can rearrange it. So 4.876 times 10 to the minus 15 divided by 4.25 times 10 to the power 10 is going to be the mass, and it gives me the mass in kilograms. It says here, it helps me out here, mass is in kilograms, so I've got it in kilograms. Now then, I can work it, that's for one particle, by the way. This is the mass of one particle. We're only talking about one particle going down the tube. So if I multiply by Avogadro's number, 6.022 times 10 to the power 23, I'll work out the mass of 1 mole of particles. It's in kilograms, however, so to get kilograms down into a lower unit value of grams, taking kilograms, a larger unit value, down into a lower value, then I'm going to multiply by 1,000, so 6.91 times 10 to the minus 2 multiplied by 1,000 to get down into grams is 69.1. And it should be a whole number. Use the information to calculate the mass in grams of 1 mole of these germanium ions. Use your answer to state the mass number. So the mass numbers are always in whole numbers. So let's scale it up to 69, and that is your answer. If it's an ion, if it's a plus ion, it's lost an electron during electron impact, and an electron has got a negligible value, so it's not going to change that number by very much. So 69 as a whole number.